Thank you, everyone, for attending today's webinar, Complying with New Functional Safety Standards, brought to you by Design World Magazine. We would like to thank our presenter for being here today, Jacob Voigt from the Eaton Corporation. I am Natasha Townsend, Associate Editor of Design World, and I will be your moderator today. Just a couple of housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, you can use the hashtag DWWebinar. We will have a question and answer session after the presentation. Go ahead and submit your question, and we will ask them after the presentation. Questions can be asked using the GoToWebinar on your screen. Jacob Voigt is a product manager for IEC Power and Logic Devices at Eaton. Mr. Voigt has a bachelor's degree in electrical engineering from the University of Wisconsin-Milwaukee. And without further ado, I will hand the mic over to Jacob.
Hello, everyone. Again, my name is Jacob Voigt. We're going to talk a little bit about functional safety today. A real good way to look at what we're going to talk about today is the questions I hope to answer. So, look at a general definition of functional safety, what it means as a definition and to people building machines. What is happening in the functional safety market, what's driving its adoption, and who's looking to it as a standard. If I am building a machine or if I have a machine, what standard should I use for that machine? And what do I have to consider when applying that standard? So what things am I going to run into? How do I determine what level of safety is appropriate for my machine, for my specific application? We're going to go briefly into what values go into a calculation, and we're going to kind of walk through and just as a kind of an introduction to these standards and what values to expect and what things are going to come up when you're going into a functional safety calculation. So, and any other questions, like Natasha mentioned, that you have along the way, you can submit via the question feature. Otherwise, we'll take them at the end. So what is functional safety? Up on the slide there's kind of the complete definition per the machinery directive of what functional safety is. The important part to understand is that it's just part of the overall functional safety of the machine, and it has specifically to do with the machine and its function. Saw blades that turn, doors that open and close, presses that come up and down. So whatever the function of the machine is, that's what we're looking at to make sure that as the machine functions, it remains safe to the environment and the operator. Another good way to look at what functional safety is what it is not. So, we're not talking about arc flash grounding, any kind of short circuit or motor protection. There are all sorts of obviously electrical safety, and the link there if you're interested in any of those. But those are not what we're talking about in functional safety. So what is happening in functional safety, specifically in North America? So you can identify a few different drivers. The first of those is from an engineering standpoint. So a lot of engineers are adopting these global or European functional safety standards to the point of having standards to design to. So there's not a lot of North American-based standards that provide a lot of guidance when it comes to control systems and designing reliable functional safety control systems. So they fall back to these standards as a way to help them walk through the process and determine what it is best that they should be doing. From a customer standpoint, selling machines or using machines in Europe where it's required for a CE mark, addressing functional safety is required to put a CE mark on a machine, and selling machines to North American customers, North American plants, North American facilities, locations that are now requiring safety assessments. So again, kind of from that engineering level, people who are looking to these standards for ways to assess how safe a machine is. And then corporate-based drivers, North American companies that are owned or managed by European parent companies. A lot of time it's in their corporate guidelines, their safety guidelines to have these functional safety standards addressed, and also as a way to limit liability. So again, having defined standards that they can fall back to and see that they can have functional safety addressed on their machines. The presentation I'm going to go through today, all of the colorful graphics and the descriptions can be found in more detail in the Eaton Safety Manual, and a link down there at the bottom. The safety manual, the front half of it is application examples, and the back half of it is all of what I'll go through today in a more expanded form, going through detail, calculations, and those things. So the first question is, which standard should I use for my machine? So this is the kind of the big CE umbrella, if you will, everything that fits under the CE mark. And one section that kind of where we drill down is into machinery safety. So we're down into this specific section. And underneath that, when you get to safety, you have different types of standards. So the type A are the high level and the risk assessment. So basic terms, general principles for design, and ways to do a risk assessment for your machine. Those are considered type A standards. They're overarching and they apply to all machines. The next type is given as type B. So these are standards that look specifically at functional safety as it applies to the control systems. And we'll talk about when you get into those, when you get into that type B. And at the bottom, you have type C standards. A type C standard is typically for a specific machine or a group of machines. So a machine that performs a certain function, maybe it's a bottling machine, may have specific standards that apply to that type of machine that do not apply to others. So, driving down further, when do I get to those type B standards? When do I use them? This little flow chart here, you start the process and you do a design per 12100 and a risk assessment per 14121. And you determine, the limits of the machine, identify any hazards that may be present in your machine, estimate and evaluate those risks. When you're done with that process, you will have a question: is the risk reduced adequately? Have you eliminated the risks that were present in your machine, or are there no risks present in your machine? If the risk is reduced adequately, you can end the process at that point. If the risk is not reduced adequately, you go to the next step. So you're looking at inherently safe design, so basically designing out the risk from your machine, adding technical protective measures, or taking use of user information to limit the hazard that's present there. If you used, so number 2 there, technical protective measures, that could be such things as guarding around the device or a door covering a hazardous area, additional e-stops on the machine, rope pulls, devices such as that. If any of those protective measures that you've identified that are going to make your machine more safe, if any of those depend on the control system, so the electronic control system of the device, then you're going to go, that's where you get into the type B standards. So that's where we go through ISO 13849 and IEC 62061, addressing those standards and how they affect your control system. So we've gotten down to type B, and now we have 2 standards. You have IEC 62061 and ISO 13849. These are both kind of under the parent safety category of IEC 61508, but they provide simplified and documented approaches to addressing functional safety on a machine. So from the beginning of addressing what level of safety you should design to, calculating all the different parameters of your application, and giving you an end result and comparing that to what level of safety you needed. While they accomplish the same thing, it's done in a slightly different way. One of the primary differences is 62061, and its generic form applies to electrical, electronic, and programmable electronic systems. ISO 13849 specifically addresses hydraulic, pneumatic, and electromechanical systems. So it allows itself to work in applications where it's other devices other than just electronics. So next couple slides here, I'm going to go through specifically ISO 13849. As I said, they go through a similar process. They use some different values, and I'll have a summary slide near the end showing how the process is kind of similar to go through IEC 62061. If you have all the information available to do a 13849 calculation, it's likely that you have all the information available to do an IEC 62061, just sort of a different process. So the questions you have to ask or be able to answer when going through an ISO 13849 calculation is which necessary safety functions are going to be performed. So are you going to have an e-stop circuit? Are you going to have a light curtain, zero speed monitoring? What safety functions will the control system be required to perform? Which properties are required for the safety function? So what is it that they need to do? Which performance level is required? So, again, what level of safety do you need to design to? We'll go through that. which safety-related parts perform the safety function. So you know what functions you need, but what components play into that? Do the contactors play into that? Do the light curtains play into that? Do the push buttons play into that? And making sure all the different parts are considered. After you go through your calculation, what performance level did you achieve? So you take all the factors into consideration. What performance level did you come up with? And then was the performance level for safety functions achieved, right? So did what you say you achieved match what you said you needed to achieve? So the first question there, how do I determine what level of safety to design to? And ISO 13849 provides this chart. There's 3 questions, the S, the F, and the P. And depending on how you answer those questions, it's going to take you to a protection level, or PL. In this case, it's the PLR, or PL required. So that's A, B, C, D, or E. So the first question is severity. You choose S1 if injuries are reversible, such as cuts or bruises. You choose S2 if injuries are irreversible, such as loss of a finger, a limb, or even a fatality. So you can see right off the bat there, if the injuries are irreversible, so just cuts and bruises, the highest protection level you'll be needed to design to is a C. And vice versa, if the injuries are irreversible, the lowest level you could have to design to is C. The second question is frequency. So if it happens less than once an hour, you can choose F1. If it happens more than once per hour, or it's consistent or persistent, happening all the time, that's an F2. And the final question is probability. So if there's a reasonable chance that you can avoid the hazard, the user can avoid the hazard either in the way they use the machine, perform service on it, or in its normal operation, that's a P1. If they're exposed to the hazard and in the way they use or operate or perform maintenance on the machine, they cannot avoid it, that's a P2. So you answer those 3 questions. You would answer these questions about each specific hazard that's apparent on the machine. And then every safety function that's designed to perform against that hazard would have to be designed to whatever the highest level it was determined for that hazard. So if you have 3 different hazards and they all require 1 safety function to protect from them, you get 1 C and 2 different E's. You do have to design to E for that safety function, obviously. So we've determined what level of safety we need to design to. How do we determine what level of safety we have in our machine? So what values go into calculating what level of safety we have? So there's 4 different things. It's the control architecture, otherwise known as the category. And a kind of a side note here, if you're familiar with EN 954, that standard did expire at the end of last year. That standard mostly defined categories and did not go into MTTF, diagnostic coverage, or common cause of failure, so any of the other data that 13849 builds in. But categories, so it's category B, 1, 2, 3, or 4, in EN 954 are the same as categories in ISO 13849. So if you're familiar with those, that's the same as the control architecture here. MTTF is the mean time to dangerous failure, so it's an engineering calculation that allows you to kind of put a number to how reliable the components you're using are. DC, or diagnostic coverage, is the percentage of faults that you're going to diagnose, so a percentage of dangerous faults that you're going to detect versus allowing them to create a hazardous condition. Common cause of failure. A common cause of failure is something that, like it indicates, it can cause failures in multiple parts of the control system. So, for example, over temperature could cause a couple of different components in a panel to fail. That would be considered a common cause failure. And then you take those 4 metrics and you combine them together to determine what the protection level you achieved is. At this point, introduce something that can kind of help you along the way here. That is SISTEMA software. This is a third-party tool that's provided by the German company IFA, available for free online. And the purpose of this tool is to kind of help you walk through and do an ISO 13849 calculation. Component manufacturers such as Eaton would provide what's called a SISTEMA library for this tool. And what that allows you to do is kind of click and drag, if you will, Eaton's components and all their safety metrics, all the things you need to know about that component, click and drag it into your application and build your architecture. So we provide a SISTEMA library with all our components in it that can be used in this tool. For example, this is how SISTEMA would help you go through and do a performance level required calculation. So what we just performed, it shows you the the 3 questions on the right side here, and then you simply check the boxes for severity, frequency, and probability, and it tells you what protection level you end up being required of you for that hazard. So again, walking you right through that process, pretty simple thing, and helps with documentation as well. So control architecture, first and probably the most important part of achieving a 13849 application. So here's kind of a chart so you can see visually, the different performance levels required on the left side, so A, B, C, D, or E, and what category you need to achieve those different performance levels. So let's say, for example, we had an application that required performance level E. We can look over to the right there and see that we need either a Category 3 or Category 4 control architecture. So we know right off the bat what control architectures are available to us. So what are the different control architectures? So the first one is B. B is simple input, logic, output. So some type of device, maybe an E-stop, normally closed contact block on an E-stop. Input would go into some kind of logic, maybe just a master control relay. It would control some kind of output, maybe a starter on a motor. So just the basic input, logic, output. And then really the only requirements for Category B is that the system shall, as it says there, as a minimum, be designed in accordance with the current state of the art. So you're using modern components and that are not that are designed for the application they're being used in. You take a step up from there to Category 1. Category 1 still has the input, logic, output structure. So same very basic structure there. The requirement here is that the safety-related parts of the control system, so the components you're using here, must be designed and constructed using well-tried components and well-tried safety principles. So you're using products that are designed for use in safety applications. A good example of that would be using limit switches or E-stops that have positively opening contacts. So, for example, on an E-stop, what that means, if you press the front of the E-stop, your force applying to the front of the E-stop is being directly translated into force that's being applied to the contact block, so that even if the contacts are welded shut, if you push the front of the E-stop hard enough, you're either going to destroy the contacts or they're going to open up. So you're not building tension on some type of spring mechanism that's between the two. Your force is going to go directly open those contacts. Category 2 begins to add in some other components. As you build upon these categories, you always have the requirements of Category 1, so you have to use well-tried safety components and well-tried safety principles. Category 2 adds in test equipment that's going to go out and periodically check your input, your logic, and your output, make sure that they're in a functioning condition, everything's going correctly with those, and output that data to some test equipment. In a Category 2, it is possible that a hazardous situation could occur in between the checks on that input, logic, and output. Then the more common ones, when you look at a functional safety, typically when people look at designing to higher functional safety, they're looking at Category 3 and Category 4. Category 3 very simply adds redundancy. So you have 2 channels of input, logic, output. And kind of the definition here is a single fault in the safety function does not lead to the loss of the safety function. So I'm sorry, a single fault in the control system does not lead to the loss of the safety function. However, an accumulation of undetected faults, so if you have a fault in input 1, input 2 will still take the circuit offline, but then you could also have a fault in input 2, and then you would have a hazardous situation. And then obviously building upon that is Category 4. So again, any single fault cannot lead to the loss of the safety function, and then the addition is, and it must be detected before the next potential danger. A good example of that is if again, we'll use the E-stop, safety relay, and then contactor example. If you have an E-stop and one of the contactors welds shut, so let's say output 1 contactor is welded shut. For whatever reason, you hit the E-stop and shut down the machine. when you turn that machine back on, if the output 1 contactor is welded shut, the safety relay must detect that. It's monitoring that output 1, detect that that contactor is not in the correct state that it should be when starting up, and then it will not allow you to start the machine back up. So that's detecting the fault before the next potential danger. So those are the control architectures. You'd select which control architecture you need based on components you have available and what level of safety you need to design to. The next thing you want to look at is MTTFD. That's mean time to dangerous failure. It can be different than MTTF. An MTTF considers all failures, both safe failures and dangerous failures. An example of a safe failure would be in a contactor. If the coil fails and the contactor can no longer pull in, it's assumed that the contactor not being able to pull in, not being able to turn on its load, maybe it's a motor, not being able to turn on that motor, that does not present a dangerous condition. So that does not constitute a dangerous failure. The contactor welding shut and not being able to turn off the motor would be considered a dangerous failure. Eaton and other manufacturers provide MTTF or B10D values in their documentation. Here's kind of an example of that. If a B10D value is provided, which it typically would be for things like a contactor, limit switch, safety, e-stop, typically provided for components in which you don't know the number of times it's going to be operated typically. So just that B10D value divided by 0.1 times the number of operations per year that that device is expected to see will give you the MTTFD value. Then you just use this equation right here to add up the MTTF for your input devices, MTTF for your logic devices, and MTTF for your output devices to get a total MTTF for your channel. This is a much simpler activity in SISTEMA, as we mentioned before. You can click and drag a component from a SISTEMA library or enter in the parameters yourself. But it shows here this B10D value was pulled in from the component. I calculated a 1,760 cycles per year. That's how many times that we operated per year. And it yielded me this MTTF value right here. I'll also go ahead and break that into 3 categories, either low, medium, or high for your MTTF level, and provide that right here. Diagnostic coverage, again, diagnostic coverage is the percentage of dangerous failures that you're detecting. So if you remember in a Category 4, any fault is required to be detected. So by its nature, to qualify for Category 4, you have to have a 99% diagnostic coverage. It does not allow you to do 100. But then for a Category 3, or in some cases a Category 2, you can have a certain percentage of diagnostic coverage. So you may have a 60% diagnostic coverage or a 90% diagnostic coverage. So how you do that diagnostic coverage, basically you need to have the diagnostic coverage of your input. So how many of the possible faults that could occur in your input device are detected, either 60, 90, or 99%, whatever that number is, divided by the MTTF of that value. So it's weighted based on its mean time to failure. Again, for the logic and for the output, and that'll yield you an overall diagnostic coverage for the entire channel. Again, a simple activity in SISTEMA as well. You'll be given a library of possible diagnostic coverage means for different types of components, and you select the type of monitoring that you're doing on that component, and it'll help you determine what your diagnostic coverage value is. And then finally, the common cause of failure. This is a fairly simple exercise. ISO 13849 provides this chart. It's a little more expanded in their standard. This is a version we have documented in our safety manual. And you basically go through these different items, and you give yourself all of the maximum possible points or none of the maximum possible points, depending on if you've accomplished that activity. So for example, under number 6, environment, If you've designed your machine with insensitivity to all relative environmental influences, which means you've made sure it can withstand the temperature and shock and vibe and humidity that it's going to be installed in, you can give yourself 10 points. And you go through all the other different categories: over voltage, use of well-tried components, implementation of training for designers and fitters, all the different things that could cause common failures throughout the machine. And you're required to get 65 of the 100 points. So this value, the value that comes out of here, does not build itself into any kind of mathematical equation. It's not a weighted thing. It's basically a check mark. You've either accomplished it or you have not. Similar activity within SISTEMA. You just go into the different categories, grab the CCF measures that you've identified and you've addressed, and load the selection into your application. And then finally, you've determined what all those different things are, and now you have to examine the relationship between them and what protection level that means you achieved. So you can reference this chart here. So again, protection level required on the left column here. Categories across the bottom with their diagnostic coverage. So you can see here, for example, on a Category 3, I can either have a low or medium diagnostic coverage. By definition, a Category 3 with a high diagnostic coverage is a Category 4. So that's why you see Category 4 here with high diagnostic coverage. So if I did a Category 4 circuit and I've achieved my high diagnostic coverage, I know that I can achieve a protection level E. The color bar plots here are the MTTF values. So as we mentioned, it's high, breaks into 3 categories: high, medium, and low mean time to failure. So you can see if I had a Category 3 circuit, but only a low diagnostic coverage, the highest protection level I can achieve is protection level D, as shown here. Very simple in SISTEMA again. This little graph will be down in the lower left-hand corner of the application throughout the process. It's going to tell you the top line there, PLR is the PL required, so what you determined via that chart you needed for a protection level. And then as you go through the system, once you have all the information in there, it's going to tell you the protection level that you've achieved, or the PL. So in this case, it's showing that a PLD was achieved when a PLB was required, so that this application would be sufficient because D is higher than B. Similarly, for a 62061, so you do a risk assessment. It's a very similar process, but takes into consideration some different things for 62061. Then you do a control architecture. So the control architectures are slightly different, but have the same kind of basic of redundancy in monitoring, elevating your level of safety. And then the values that you need to calculate to come to a conclusion is a little bit longer for an IEC 62061 application. So you're looking at your dangerous failure rate, which is similar to an MTTF, a diagnostic coverage, again, similar to the diagnostic coverage in 13849. Common cause of failure, so there's items you have to address to make sure you're not susceptible to a common cause failure. Proof test or lifetime, so how long the machine is designed to be in use, or how long it'll be before it's overhauled, if you will, or all the necessary components are replaced. Diagnostic test interval, so how long between tests are all the components being tested. Sometimes that diagnostic test happens when the machine shuts down and comes back up. Sometimes it happens periodically through its operation. The probability of a dangerous failure, so how probable is it that some type of dangerous failure is going to occur based on the reliability of the components. You'll get a SIL, or a safety integrity level, for the subsystem. You'll get a safe failure fraction, so what percentage of the failures are either safe failures and do not affect the safety function, or are detected. So this will add the number of safe failures plus detected failures divided by the total number of failures that component's possible. SIL claim limit based on that safe failure fraction, and then the lower of your SIL for the subsystem and your SIL claim limit will determine the SIL, the safety integrity level of the entire system. So it's a similar process. You use similar values to go through and do the calculation, but use a slightly different process. Okay, so to go through kind of a couple application examples here, finally, is so for example, if we had a dual channel emergency stop and we wanted to have redundant series contactors, we wanted to have a monitored manual restart. What that means is when the machine shuts down, you're going to have a manual restart, so you're going to require to push a button basically to restart the safety function. And what the monitored part means is that the safety relay being used here is actually going to go out and make sure that that reset chain changes states. So if it's in the closed position right away when it's looking for a reset, it won't reset. It will wait till it goes from the closed position to the open position and back to the closed position before it resets. Cross-circuit recognition. So we're going to use a dual channel e-stop. So we've got two channels, so two normally closed paths on the e-stop, and we're going to monitor to make sure that there's not a short circuit between those two paths, as those wires are for quite the distance are going to run very close to each other. We want to make sure that there's not a short circuit that's keeping us from detecting an emergency signal, and the safety relay is going to do that by sending out a different voltage over both the channels and ensuring that it sees the correct voltage on the correct channel. We're going to control three different motors, and we'll show that in the power diagram, which is some simple push-button start-stop control. We determined based on the hazards of the machine that we need to design to a protection level of E. So sorry this is a little small here, but I wanted to fit it all in one slide. So this is what your control circuit could look like. Inside the dotted line here in the center is the safety relay. First off is the e-stop up here. So this is our two-channel e-stop. So one channel is here between S11 and S12. The other channel is down here between S21 and S22. So again, these two channels are going to have different voltages on them so that it can detect if there's a short circuit between the two channels. Performing the reset function is over here. So we're monitoring normally closed contacts, auxiliary contacts, on each of the four contactors that are involved in this application. What this will do is, if any of these contactors have welded shut, these mirror contacts, these are specifically designed to monitor the main power poles and always be open if any one of the main power poles is closed. So that's a mirror contact. These four will, again, ensure that the contactor is not welded shut. If the contactor is welded shut, this would be open and it wouldn't allow the safety relay to reset. And then down here in the bottom is our manual reset button. So this would be typically just a blue push button on the panel that the operator would have to press, which would completely close this path between S33 and S34 and provide a reset signal to the safety relay. And then finally over here on this end, this relay, the specific relay, has three normally open safety outputs. So for example, between 13 and 14, you'll see on this normally open output that there's actually two normally open contacts in series that make up that. So if any one of those contacts failed, the other one would still open and still interrupt power to this contactor coil right here. So this coil will represent the upstream contactor. We'll see that in the power diagram. And these other three coils here, wired with the start-stop circuitry, will represent the three downstream contactors. The upstream is on one path, so the 13, 14, and the three downstream contactors are on another path, here 23, 24. The power diagram for this, again, so here's the upstream contactor, and then here's are the three. This device here would be the motor controller, so providing short circuit and overload protection, and then the contactor providing control. The reason there's an upstream contactor is because we want a protection level E, so we designed a category 4, which means we have to switch off, we have to have redundancy, right? So if this contactor welds shut, we need another way to open up so that this motor turns off, and that's this upstream contactor up here. So that will provide redundancy for each of these three motors. When you go through the calculations, our structure that we used there was a category 4. Our MTTF, when you add up all the MTTF of the various components, would come out to 100 years. the B10D values and the number of operations that we used in those calculations for the different components. Common cause of failure, obviously this is kind of a fictitious application, but we are assuming we achieved a 80 for a common cause failure. We have a 99% diagnostic coverage. We're detecting all possible dangerous failures that could occur, which means we're able to achieve a protection level E. And you can see down there in the lower right-hand corner, in this application, you could have achieved protection level E using a category 4. This would have also qualified for a SIL 3. This is an example of the type of application that is in the front half of the Eaton safety manual. Goes through a couple of these different applications and shows how these calculations are done. One more example here. So a single channel this time. We're going to do a position switch or a limit switch. We're going to do a monitor manual restart again. We want to control 2 motors, but we're going to handle the safety circuits and the push-button start-stop control via a small safety controller or safety control relay. So kind of a, if you're familiar with a configurable relay, similar concept but with safety ratings on the device. Based on the hazard apparent here, we're going to use a protection level required of C. So similar control diagram here. This device here obviously is the safety controller. So on the top side here it's got 14 safety inputs, and on the bottom side here it's got 1 relay and 4 transistor safety outputs and 4 test signals. Right here is our single channel limit switch of just a single normally closed contact. We don't need to go to a dual channel because we only need to achieve a protection level C. Right here we have the reset chain, so this is going to give us again that monitored manual restart. We're monitoring these aux contacts on the contactors, normally closed aux contacts, and we're going to reset via this normally open push button here. Start and stop functionality are being fed directly into the safety relay. And then on the bottom side, again, here an upstream contactor and 2 downstream contactors coming off of 3 of the safety outputs. The power diagram, again, very similar to the first one, upstream and downstream contactors for each motor load. Calculations for these, so this is a category 1. We do have redundant contactors, but important to point out here, because we just have a single channel on the input side, we cannot qualify for category 3. We're maxed out at category 1 because we have a single channel in 1 point. But we do have a high MTTF because we're still using very reliable components designed for safety applications and safety principles, showing there the B10D and the number of operations we use. Common cause of failure. We determined a diagnostic coverage of 97% there based on which of the dangerous faults on the input circuit we could detect, which gave us a protection level of C. And you'll see this is a category 1 and would qualify for a SIL rating of 1. Okay, so that's the extent of my presentation for today. Hopefully that's enough of an intro for you guys to be a little bit more familiar with functional safety applications, what it means, why it's being driven here in North America, and some of the things you need to go through and be aware of when you're doing a calculation.
Well, thank you, everyone. We will now open the remaining time for questions, but before I do, I would like to apologize for Jacob for mispronouncing his name. His name is Jacob Fuchs, and he obtained his bachelor's degree in electrical engineering from the University of Wisconsin-Milwaukee. Mr. Jacob.
Yes.
I would like to ask you first, can you refer us to any documentation, application examples, or technical drawings for more information? Technical data, yeah.
As I mentioned during the presentation there, we do have the safety manual available, which is a really great place to start when you're looking for application examples, as well as some detailed guide to a way to walk through the standards and how to do a calculation. Real quick way to get there is eaton.com/FS for functional safety. In addition, on there you'll find some a link to our SISTEMA library for some of that additional technical detail. and some other PDFs about data and information you'll need for doing a functional safety calculation.
Okay. And second question posed, how are functional safety standards evolving?
Yeah, so one of the primary things is the different standards that are coming up. So again, as I mentioned in the presentation, EN 954 was a functional safety standard for a very long time, became very popular, only addressed control architecture. So they were concerned that that standard did not take into consideration the reliability of the components, the diagnostic coverage achieved, or the common cause failure. So they built kind of the 13849 standard around that. At the same time, a similar standard was being built, the IEC 62061 standard, that did things just a little bit differently. There's already a kind of a technical report drafted as far as how they're going to combine those standards. But I think one of the important things to recognize is that eventually in the functional safety world, we'll be looking to a new standard that'll define a kind of a collaboration and a combination between the 13849 and the 62061 standard that are there today.
Okay, thank you. And I have one more question. As control system architecture shifts and communication capabilities expand, how do these changes impact functional safety considerations? For example, how does an integrated HMI PLC impact functional safety applications?
Yeah, I think one of the important things to recognize is, right now to a lot of machine builders and their control systems, safety is a bolt-on. So they have their standard control, their PLC, or their HMI, their operator interface, whatever is performing the logic, the SCADA, all the advanced functionality. And then the functional safety is kind of bolt on to that. So you have a safety relay or a small safety controller that is kind of bolted onto the side of that application. And as things evolve here, people are going to have to consider moving more towards products that can be used in both their standard and their safety applications to perform that more seamlessly. So whether that's in their communications network and moving to safety communications network, or moving to advanced devices that can perform that safety functionality, I think it's important for machine builders to recognize that safety is going to become an integrated part. It's not going to become a bolt-on. It's going to become necessary for every part of their machine.
Okay, well, that does it for all the questions. I have one more question.
I think he's looking for the information
first slide.
about the recorded webinar. Yep.
Okay. Well, if there are any more questions for either me, Natasha Townsend, or for Jacob Fuchs, will you please send your questions to me at NTOWNSEND, that's N Townsend, at WTWHmedia.com. Or you can send your questions to Jacob B. Fuchs at JACOBBFEUTZ@Eaton.com. Thank you, everyone, for attending this webinar from Design World. This presentation will be emailed to everyone later today and will also be available at www.designworldonline.com. You can tweet with hashtag #DWWebinar, or you can connect with Design World at Twitter at Design World, Facebook at facebook.com/Engineering Exchange, on LinkedIn at Design World Group, on YouTube at youtube.com/Design World Video. And you can also discuss this webinar on engineeringexchange.com. Thank you kindly. Have a great day, everyone.